Hello, everyone. I'm Hao Teng, a PhD student at the CS department of Purdue University. Today, I'm going to introduce our recent work, algorithm and system co-design for efficient subgraph-based graph representation learning. This is a joint project with my colleagues at Purdue, PKU, and Cornell, and supervised by my advisor, Professor Peng Li. Next, I will present a novel subgraph-based framework for large-scale graph learning tasks. Let's get into it. Graph structure data are everywhere in our daily life. It is a collection of interlinked descriptions or relations among entities. For example, the people you connect with on LinkedIn and other social media also have other forms of connection, which constitute a social network. Transactions like shopping on Amazon, ordering food through Uber Eats, create an e-commercial network between users and products or services. In addition to this, graphs are widely used to formulate problems in scientific studies, such as transportation networks and presenting protein or molecules structures. With the availability of a massive graph data, graph learning algorithms and their applications have become trending topics recently. In general, all graph tasks and applications covered in today's talk can be formulated through subgraph representation learning, defined as follows. Given a query set of nodes Q and a surrounding subgraph GS, subgraph-based graph representation learning aims to learn a mapping from GS to some predicting labels. That is to decide the property of the node, to predict whether there are missing links between two nodes, or to detect whether a group of nodes form a community, through learning the surrounding subgraph of a given query. In our work, we focus on the later two tasks that are more complex and challenging. In the following 5 sections, I will present a novel algorithm system co-designed framework for scalable and efficient subgraph-based representation learning. First, we would like to investigate why should we use subgraphs. Here is a toy example for friend recommendation, which is a fundamental application of link prediction. In the given graph, is user A more likely to be friend with user B or E? Graph neural networks are one of the most popular and promising models nowadays to answer such a query. It automatically encodes graph structure and node features through message passing and neighborhood aggregation, and then generates vectorized node representation for downstream tasks like friend recommendation here. However, if we use GNN for this task, it can be really risky due to its limited modeling power. Here, node B and node E are symmetric, and their unfolding computation subtrees of GNNs are in fact identical. That is, without additional information, GN will give the same answer for user B and user E for this query. Such behavior would pose critical issues for GN-based recommendation systems. Additionally, recent works have shown that GNN are limited for modeling complex relations and high-order patterns. To add more nonlinearity, using deeper GNNs come with a larger but possibly unnecessary receptive field, which pose the risk of contaminating the representations with irrelevant information. Thus, people turn their attention to subgraph-based method that addresses the limitation of neural networks mentioned earlier. For a given query, it first extracts a subgraph surrounding it and then learn the representation of the extracted patches for final prediction. For this friend recommendation query, through the extracted subgraph GS1 and GS2, it clearly tells the difference. The user B is more closer to user A than user E. By pairing distance features, there's subgraph-based methods can have more expressive power. Meanwhile, it distinguishes the depth of a model and range of receptive fields as the input is just the extractor subgraph itself. In practice, it has shown superior performance on tasks such as link prediction, relation prediction, and high-order pattern prediction. Subgraph-based methods bring more expressiveness and prediction performance, but it also comes with a price. Current models, including WSNM, SEAL, and sub-GNN, are neither scalable or efficient. First, for each query, subgraph-based method need to perform an extraction, which either has high computational cost or need extensive memory. Secondly, in real world, no discrete follows a long tail distribution, which bring the challenges of irregular subgraph size, often referred as neighborhood explosion problem. The irregularity of M-hop subgraphs make it more challenging. Lastly, previous works of optimizing GNNs cannot be directly applied to subgraph-based models. Current algorithm designs are primitive and with limited system support. Although these motivate us to design more scalable and efficient framework for subgraph-based graph representation learning on real-world applications. In this regard, we present SUREL, the first framework adopting the co-design of algorithm and system for subgraph-based GRL. We break the procedure of subgraph extraction into multiple random walks, which can be shared across different queries and significantly improve the reusability. To address the irregular neighborhood, we use fixed size of random walks to regularize the sampled subgraph. To compensate for the structure loss after subgraph decomposition, we introduce a positional encoding technique. Overall, we use a set of collected walks and its relative position encoding as downsampled subgraphs for graph learning tasks. Specifically, we propose to decompose subgraphs into a set of random walks. The working sampling here is performed on the node level instead of query-based, so that it can be reused for different queries and be computed offline and in parallel. This design is much more scalable than extraction-based method. After the sampling procedure, the collected works lost some structural information. Thus, we introduce the relative position encoding, which encode the relative distance between nodes in the collected works and their source node. Here, we use the landing frequency of random works as the value of RPE, which leads to similar express power as other subgraph-based models and is more powerful than standard GNNs. Next, I will illustrate the pipeline of SUREL step by step. First, it performs the preprocessing offline and in parallel. That is to decompose node-level subgraphs to set of works that is corresponding relative position encoding. For a given query, as here, it calls the join operation to concatenate the node-level structural features to a query level, including sampled set of works and their RPEs. Then we employ a neural network to learn the assembled subgraph and generate its representation of the query for model serving. Through the optimization techniques, including parallelization, memory management, and loading balance, SUREL achieves a significant improvement on scalability and efficiency of SGRL on large-scale graphs. Next, we evaluate our proposed framework and other baselines extensively on two types of tasks. Link prediction, that is to estimate the likelihood of a link between two endpoints in a given graph, which can be further generalized to predict a type of links, such as relation prediction on heterogeneous graphs. Another task is a high-order pattern prediction. That is to predict whether the set of nodes will foster a cover edge in the future, which is referred as a hyperedge. All these models are tested and evaluated through Open Graph Benchmark, which is a collection of realistic, large-scale, and diverse benchmark datasets for machine learning on graphs. We selected 3 link prediction and 1 relation prediction datasets. Citation2 and Colab are social networks of citation and collaboration. PPA is a protein interaction network. OGB-MAG is a heterogeneous network which contains 4 types of nodes and their relations. For high-order datasets, DBLP co-author is a temporal network that records co-authorship of papers as tempo-stepped high-order links. TaxMath contains a set of talks that are applied to mathematical questions on website as hyperedges. All these datasets have millions of nodes and/or edges that reflect the needs and challenges for real-world application on large-scale graphs. Here, we present the prediction performance for link prediction on OGB. As we can see from Table 3, SUREL achieved around 50% performance boost than traditional graph embedding methods and standard GNNs, and have a comparable or even better performance than SEAL, which was the state-of-the-art subgraph-based model for link prediction. For relation prediction and high-order pattern prediction, SUREL achieved up to 60% improvement than standard and relational GNNs. It has even better performance in high-order cases, where other traditional SGRL model, like DGNN, suffers from severe scalability issues. As for scaling performance, we measure the runtime, memory consumption, and inference throughput for all the baselines. Compared to canonical GNNs, SUREL can match their training time, but we acknowledge that it is still slower for inference. However, standard GNNs can only achieve subpar prediction performance on these tasks. Within SGRL-based models, SUREL achieved 5 to 20 times speed up than SEAL on inference and greatly reduced the memory pressure. To summarize, SUREL is a novel algorithm system co-design framework for subgraph-based representation learning. It achieved a state-of-the-art performance on 3 graph benchmarks with up to 20 times speed up and around 50% performance gains than other baselines. It can be deployed to different types of graphs with millions of nodes and edges on multiple prediction tasks for link, relation, and high-order patterns. It also has the capability and great potential in recommender systems, scientific discovery, and many other subgraph-level tasks. If you are interested in our work, please check our paper. Our code is also publicly available on GitHub. For any questions, please feel free to reach me through the email attached. Thank you.